Hello, my name is Alejandro Delgado, and this is my lab on motion of a falling object. In physics problems, we consider the problem to exist in a very perfect world without air resistance and sometimes even without friction. However, other forces exist, such as drag, that interfere with the motion of this falling object. In this lab, I will be analyzing the motion of a falling paper greeting card in the case where gravity is the only force I consider in the surroundings, and in the case where the drag force is accounted for. The system is a greeting card, and the surroundings are the force of gravity and the force of drag. Some fundamental principles I used when considering this lab is when undergoing constant force, V is equal to V average, as in V is equal to the final velocity plus the initial velocity over 2. When undergoing non-constant force, however, V is equal to the final velocity. The drag force is dependent on the velocity, as the equation for the drag force is F net is equal to B times velocity squared in the V hat direction, which will be shown later. The B proportionality constant in the drag force depends on equally on the object and as the environment, and gravity is always the constant force. Because the object is supposedly falling in one direction, just downwards, I'm going to be looking solely at the y component. Although it did move a little bit in the x component, we could just ignore that. Here's the video I used. When put into tracker, this is the results that we got. It's a curved motion, and that makes sense because drag is accounted for in the scenario as it's a video, and you're able to see this through the kind of way that it sways around. It doesn't fall at its complete speed that most heavier objects do. After all, it is a paper greeting card, and that was the point. That was the reason I chose it because I knew it wasn't going to fall completely straight. You can see the data here, and it does show a curved path. So prior computations I made before putting it into a computational model in order to kind of create and add values in is the initial position of the ball, which will need to be added, the initial velocity of the ball, which is helpful for of course, the initial velocity, and also for finding the average velocity in the case where we're only considering the gravity force, where we need to find the average velocity. The same thing applies with the final velocity, which was used for in both scenarios where the non-constant force is accounted for, where velocity equals to final velocity, and in the case where average velocity was vi plus vf over 2. Here's the computational model for the ball, I mean not for the ball, for the paper greeting card as it falls through, and gravity is the only only force acting on it. And this makes sense. The velocity is a constant line because there's only one force acting on it, and it's a constant force. So this force theoretically should be the weight of the greeting card, and it's sloping downwards because it's falling down. And here's the computational model with drag, which is a little bit different and it actually shows a little bit slower than the other one. And this is because the drag force points in the opposite direction as the velocity of the ball, meaning that the ball is falling downwards, the drag component works upwards, resisting the ball. All in all, when gravity is the sole force acting on an object, the object falls due to constant force with a constant acceleration, as we saw in the previous graphs. When drag is introduced, however, a non-constant force acts on the paper. Some sources of error include the ball not falling completely straight down, inaccurate mass, it was hard to measure a paper greeting card, and inaccurate length of card. The point of terminal velocity is the point in the object trajectory where there is no more acceleration. This would be part of the graph where the curve becomes constant. However, the terminal velocity is not dependent on anything else other than the weight of the object, because if the object was thrown initially downward, the terminal velocity would be the same, since the value of the terminal velocity has nothing to do with the gravity force. Sorry, the terminal velocity has everything to do with the gravity force and nothing to do with the initial velocity.